are going to talk a lot in detail about insulators and conductors. You have the definition here for you. We did discuss it a little bit last class, so you should have an idea what an insulator and a conductor is. Generally, we have everyday experiences of insulators as we drink our coffee or our ice water. So the same concepts apply when we're talking about electrical insulators and electrical conductors. So rank the different items, the different materials here, or rather than rank, actually categorize the different items. See if you can add more to the list based on your experiences. And then we've got a little theory down here, so let me know what you think. I've never heard this theory about rubber-soled shoes, but if you've heard it, it's a thing. So tell me if you think that would be true or not true. I want you to raise your hand when you decide it's a conductor versus an insulator. So we're going to start with wood. How many of you said wood is a conductor? Good. How many of you said it's an insulator? It's definitely an insulator. We can't have electricity travel through wood. Same thing, wood doesn't hold temperature very well. How about cotton fabric? A conductor? Insulator. Good. Cotton. What about a copper wire? Conductor? Generally, metals are a conductor, so copper. How about, this is a tricky one, pencil lead. Conductor, about half. Insulator, 2, maybe 3. This one's a tough one. So pencil lead is not a metal. It's actually graphite, but it is considered a conductor. So pencil lead, not as obvious, but it is a conductor. How about glass? How many say that is a conductor? Insulator? Very good. Rubber, conductor. Insulator. So the little scenario down here was kind of a hint as to what it is. It is an insulator, which is where this whole theory comes from. And we'll talk about that. Do you really think that rubber can protect you from getting electrocuted? Let's get into aluminum foil. How many of you say that is a conductor? Insulator? Aluminum foil is a conductor. And then water's a tricky one. How many of you say water is a conductor? How about an insulator? Water is actually a conductor. And that's the whole reason why they have all these warnings on like hair dryers or any of your electrical equipment in the bathroom, is because if that electrical equipment hits the water, it's going to spread through that water and electrocute you. So that kind of gives you a hint that water is definitely a conductor. Electricity does travel through water. So, did anyone have any new materials that they wanted to add to this list, whether it's a conductor and an insulator? Any thoughts, maybe from what we talked about in our lab last class? Mika?
I mean, skin is a conductor.
Skin is a conductor. Very good. We're actually going to test that today. Spencer?
Yeah. On skin, I think skin is actually an insulator, but the oil and sweat that's almost always on our skin is a conductor. Which is why people with conditions where they don't produce any sweat or oil, they can actually touch live wires and be completely fine.
Interesting. So I didn't know that, but it is the oil and sweat. We already established that water was a conductor, but that makes sense. Our body is mostly made of water, so yeah, really interesting. It's the oil and the sweat in the skin. Nice. I learned something today. All right, anything else to add? Now, let's go to this theory. Maybe something that you could use anytime you're stuck in a lightning storm. If you have rubber-soled shoes, and we already said rubber was an insulator, right? Electrons cannot travel through. Basically, the transfer of electrons is what generates electricity. The wires we have transfer electrons to give us our lights, the power to run our computers. So, if we have an insulator at the soles of our shoes, will we be electrocuted when we're standing or struck by lightning? How many of you think that this is true? Raise your hand. How many of you think it is false? Would any of you dare to test it out? Let me hear your thoughts. Mika.
Well, I know that this is true to a certain extent. Because the rubber grounds you, but if you're actually electrocuted by lightning, it kind of overcomes the threshold. But with cow wire or horse wire to keep them from moving out of the boundary, when it's on and you have shoes on, you can touch those wires. But because the horses have hooves, they're not grounded until they get electrocuted. But I was hanging out without shoes on around the horses, and I touched the wire and it electrocuted me.
You know, very interesting point. So Mika's talking about the electrical wires that you find in farms. I have a video. I wish I had it ready for today, but I'm going to present it to you next class. It's the same idea. I have a video of students, maybe students. They have insulating stools, plastic stools that they stood on, and they touched an electrical wire and they did not get electrocuted. So these stools are made out of rubber. The problem is, and it might protect you. The problem is the amount of electricity, the amount of energy that is held in a lightning bolt is really very much stronger than an electric fence. And the soles of your shoes, though they are insulators, will not be enough to protect you from that electric shock. So don't try this at home. There is one thing you do want to do. If you are stuck in a storm, what you would want to do is get into your car, because the metal around your car is something we call a Faraday's cage, and I'm going to actually demonstrate that when we have a Van de Graaff machine. How many of you have seen Van de Graaff machines, maybe saw it in middle school or elementary school? It's this big bulb that generates a lot of electricity and shocks you, makes your hair stand up. We're going to play with that next class, and I'm going to show you what a Faraday's cage does, but your car protects you from that electric shock. And so it might seem crazy, but you actually do want to get into a car if you are stuck in a lightning storm. Not under a tree, nor standing with rubber shoes on. Did you have a question, Anya?
Yeah, how does that work?
Really good question. So I had a lot of students ask me the same question. The statement says that you are physically struck by lightning. So regardless of what you're wearing, you would feel the electric shock. Well, this goes back to the concept of grounding, which Mika had mentioned, and we mentioned it last class as well. I'm going to show you, this is a simulation you're going to play around with next class. So what happens when you get shocked, and this is John Travoltage, I'm going to hold his finger up, and we just talked about conductors and insulators, right? We've got a conductor in our skin, or the oils in our skin, and we've got a conductor in this metal doorknob. If I use friction This is the triboelectric effect, where you can create a static electricity through friction and contact. So I'm building up electrons. And this is what would happen if you had your hair standing on end because of static electricity, right? You're built up with electrons. You don't feel a shock until you actually touch something. Now, air is generally an insulator, but if you build up enough charge, air can be a conductor, and electrons can travel through air. That's the same thing that happens when you're hit by lightning. You don't actually feel electrocuted until the electrons travel out into your body and then out of your body. So that transfer of electrons is when you feel that electric shock. So if you had thick enough insulating shoes, you actually wouldn't feel the electric shock unless you touched a conductor, you touched the ground with your skin, then the electrons travel on.
That essentially means that if you get struck by lightning while wearing like super rubber soled shoes, it's essentially a death sentence. Because you would eventually have to touch something.
You would eventually have to. Yeah, unless, well, yeah. I mean, that definitely don't try it at home. What the shoes will do is, even if they were super thick and super insulating, is that you can't wear the shoes forever, and you can't avoid touching. You can't avoid touching conductors, right? They're everywhere. So, really good point, Spencer. Any other comments or questions?